Hi, my name is Jenna Saylor, and this is my Physics Lab 5 on the rope swing. Starting out with the purpose of the lab, the purposes were to predict the motion of the jumper, to determine the speed of the jumper and the tension of the rope in an ideal setting, so no stretch, to estimate the stretch of a real spring or rope at the bottom of the swing, to predict the speed of the jumper and the tension of a real rope, and to answer what effect does including dampening or air resistance have on my predictions. For the preview, the system was the man, the rope, and the rock, and the surroundings were everything else. The initial conditions were as follows. The mass was 80 kilograms, the height of the man was 6 feet, initial velocity was 0, the initial position was 0 relative to what I was using to calculate, the initial length of the rope was 45 meters, and the spring constant of the rope, according to Google, was 785 newton meters. And this was just saying an average rock climbing rope, the spring constant of that. And then for the results, the speed of the jumper was 29 meters per second at the fastest point. The tension in the rope was 882 newtons, and the stretch was 46.12 or 1.12 meters. Some important concepts to understand are spring force or Hooke's law, and that basically says that force is equal to the negative spring constant times the amount of extension in the rope. And also below we just have a little extension to that law. Just period of oscillation is 2 pi times the square root of mass over the spring constant, but that's not really used in this, but it's just good to know. We also need to know Newton's second law, or the momentum principle, which states that force is equal to mass times acceleration, or change of momentum is equal to force times change in time. And then down here we just have instantaneous velocity and normal velocity, which is used to calculate the speed of the man at the maximum point. Before I show the computer model, I would just like to talk about the actual experiment. I took a video off of YouTube of the world's largest string and put it in Video Tracker and plotted the center of mass for the man as he swung across. And as you will see later, a graph is produced, but let's get into the computer model right now. Here I just updated the ball mass or the man mass to the mass of the man. Same thing with initial position, initial velocity. Delta T was just the delta T used in the video tracker, the gravitational constant, the spring constant, the initial rope length, and then right here we just have our position update formulas and our spring constants, and also just changes in energy. Kinetic energy is 1/2 mv squared, gravitational is mgy, and then spring is 1/2 ks squared, and then right here total energies is all them added together. Over here we just have a few more updates, just calculating gravity, calculating spring, calculating total net force, position update, velocity update, once again updating the spring position, and then once again updating our energies. So as you can see here, the x position and the y position, the man started high and then he lowered and then came back up, which is very similar to what a swing would do. Down here is our graph from the video. You can see it's very linear, meaning he traveled at a constant speed, but compared to our predicted ones, he should have had some sort of deviation in it and acceleration because he was starting from us. Right here we have our changes in energies as he swung or oscillated. And then over here, I was calculating the tension in the real rope. So in a real setting, the gravitational force would be pulling down on the man, and that means tension would be the opposite since there's no other forces acting if we're ignoring air resistance. So I got 882 newtons. And in the air resistance model, which we'll talk about in a few minutes, it would be slightly less or slightly more because there's additional forces being on the man. Over here is the stretch in the rope. So the spring force was equal to the tension in this case, since we're assuming that the rope is a spring. So 882 is equal to our spring constant times the initial length of the rope minus the actual length of the rope minus the initial. And right here we're just plugging in numbers and we get the final length, 46.12 meters. And then down here just calculating maximum velocity through the energy principle. So change in energy is equal to change in kinetic plus change in gravitational. And here I'm just assuming that once again the rope is a rope and not a spring. So if you take this into account, you'll get 30 meters per second. For the extended question, what effect does the dampening or air resistance have on my predictions? Air resistance would cause the person to swing with an added opposite force, causing them to move somewhat slower than they would have in perfect conditions. This causes the predicted final or maximum speed to be lower than it had the potential to be and adds an additional error in our trial, or a larger deviation between the computer model and experimental model. Finally, for errors, I have very limited coding experience, so obviously if I was more educated in coding, the computer model would be more accurate towards the true experiment. There could have been error in the video tracking by plotting the center of mass. I'm not able to necessarily plot the point in the same spot every single time, so it varies a little. We could also have used more accurate and precise numbers for the mass of the man, because we sort of just had to take an estimate since we didn't explicitly get his weight or height. And so the assumptions, and then finally, as I said before, air resistance caused an error in our data. If we had the air resistance, we would have been able to account for it in our trial and have more accurate results. Thank you.